All right, Earth Science. This is your first chance at a video lecture. We're going to do this to start off Chapter 12, looking at Section 1 as we start to investigate earthquakes. So, you guys should already have your notes out, so let's get started. Your objectives for this section, you have 4 of them. First thing is describe elastic rebound. You've heard both of those terms before somewhere, I'm sure. Elastic, as in the elastic band in your gym shorts, and then a rebound, like the thing you get in basketball. But we're going to associate this new term with earthquakes. Secondly, compare body waves and surface waves. I'm sure you've heard of seismic waves before, and there are actually several different types of seismic waves. The first 2 types of seismic waves that we're going to investigate are body waves and surface waves. Then explain how the structure of Earth's interior affects seismic waves. So specifically, things like body waves and surface waves are going to try to travel through the Earth's interior. They're not going to travel the same way and at the same speed. So you're going to try to explain how the structure of Earth's interior makes those differences happen. And lastly, explain why earthquakes generally occur at plate boundaries, right? So far we know of 3 different types of plate boundaries. We have convergent, divergent, and transform boundaries. Explain why earthquakes generally occur at those locations. Let's start with some definitions. We're talking about earthquakes in this chapter, so let's make sure we all understand what an earthquake is. It's a movement or trembling of the ground that is caused when a sudden release of energy by rocks that move along a fault. Okay, and we're going to be using this phrase quite a bit. It's a sudden release of energy. It's a sudden release of energy. Last chapter, we painted this picture of tectonic plates moving gradually all over the world constantly. And they do. However, the rock on top of them, if they're locked against another piece of rock, the rocks won't move. And so what's going to happen is they're going to have stress built up in them as the plate tectonics underneath the rocks move. It causes the shape of the rocks to change. It's stress. It's like if you were bending something or pulling a rubber band out really, really long and really stretching it out. That sudden release of the rubber band is very similar to what happens in the sudden release of energy in these rocks. It's just that in common experience, rocks aren't that elastic for us humans. But with the amount of force that is generated by plate tectonics, yes, compared to that, even rocks become elastic. Now, next term, this is part of one of your objectives for this section, elastic rebound. It's the sudden return of elastically deformed rock to its undeformed shape. Again, think about a rubber band. You have a normal undeformed shape. It's just a regular shape. But when you go to stretch it, okay, you're changing the shape. You're making it much, much longer. Now, once you snap that rubber band, it suddenly returns to its undeformed shape. So if we apply this idea to rocks, we're bending these rocks, we're deforming these rocks, but if we suddenly stop applying the pressure, if they were to just go back to their normal shape, that's called elastic rebound. Now, earthquakes occur when rocks under stress suddenly shift along a fault. A fault is a break in a body of rock along which one block moves relative to another. So if we think about something in our own backyard, the San Andreas Fault, we have a part of California that's on the Pacific plate. We have a part of California that's on the North American plate. Those are 2 blocks of rock, and they're moving relative to one another. One's moving north by northwest, and the other is not. So they're moving relative towards one another. That is called a fault. Getting a little deeper into elastic rebound, geologists think that earthquakes are the result of elastic rebound. So think about that. We have this massive amount of force being applied to these rocks. They're bending, they're bending, they're bending. But finally, at one point, one of those rocks is going to snap and break, and everything else is going to slide back to where it normally was. That's going to cause an earthquake. So in this process, the rocks on each side of the fault are moving slowly, typically. Now, if the fault is locked, which means it doesn't move, the rock will deform and the stress in the rock will increase because they're not moving to allow the stress to dissipate. When rocks are stressed past the point at which they can maintain their integrity, they fracture, they break. Right? Once you apply more force to the rock than it can handle, it's going to break. Okay? Here we call it fracture. The rocks that separate at their weakest point, the rocks then separate at their weakest point along the fault and then rebound or spring back to their original shape. And Robot Lady is going to have a video for us to watch here.
This strike-slip fault has no stress acting on it at this time. However, tectonic forces can push rock on either side of this fault in opposite directions. In this case, the rock behaves like a rubber band and deforms in an elastic manner. Elastic rebound occurs when more stress is applied to rock along the fault than the rock can withstand. When this happens, the rock slips and releases energy. Like a rubber band that has been stretched so far that it breaks, the rock returns to its unstretched shape. During elastic rebound, rock releases energy that travels outward as seismic waves and causes earthquakes.
Thank you, Robot Lady. Now, let's start to look at earthquakes and the different parts of an earthquake, the anatomy of an earthquake. First, we have the focus. The focus is the location within the earth along a fault at which the first motion of an earthquake occurs. Now, I'll tell you right now, focus is the singular form of this noun. You have one focus, but the plural form of this noun is foci. If you're talking about one focus, then you can talk about two foci. Now, the difference between a focus and what's going to follow here, the epicenter, is that the focus happens beneath the Earth's surface. Okay, that's why right here it says the location within the Earth. All right, let's move on to epicenter. It's the point on Earth's surface. Okay, there's that distinction there. On Earth's surface, above an earthquake's starting point, aka focus. Although the focus depths of earthquakes vary, right, so they're going to be at different depths, about 90% of continental earthquakes are considered to have a shallow focus. Earthquakes that have deep foci, remember foci is that plural term of focus, earthquakes that have deep foci usually occur in subduction zones. And that should match up with our understanding of a subduction zone. We have one plate being forced to go underneath another plate. And so obviously that plate is going to be going very, very deep. And so this action is going to be happening fairly deep, resulting in a deep focus. And earthquakes that cause the most damage usually have shallow foci. And so if the point of breakage, the main movement, is happening very, very close to the surface, we are going to feel as humans that force more directly because it's not being mitigated as much by traveling through the rest of the Earth itself. So the more damaging earthquakes tend to have more shallow foci. Now here you have a diagram, and again, let's just paint this in our head. Let's just assume that this is the San Andreas Fault. It's not, it's just a generic fault, but let's assume that it is the San Andreas Fault because this actually is a transform boundary. You can tell because we have the direction of this plate on the right moving up, the direction of this plate on the left moving down. And we can see the representation of the fault itself. It's just a break in these two huge chunks of rock. Now I want to point out here are some terms that we've just discussed. We have the focus. Okay, it is the origin of the earthquake, and notice it's below the surface of the Earth. That's the focus. Now the epicenter, if you hear about if you hear about an earthquake on the news, you're not going to hear about the focus. You're going to hear about the epicenter because the epicenter has more to do with what's going on with humans on the surface. Because where do humans live? On the surface, and so we are more concerned about what's going to happen to us on the surface, and the epicenter is the first place on the surface of the Earth that these seismic waves, these concentric red circles that are moving outward, the first place on the surface of the Earth that these seismic waves reach. Let's talk about those seismic waves. One of the things you're supposed to be able to do is compare body waves and surface waves. A body wave is a seismic wave that travels along the body, through the body of a medium. And that's going to be important. It goes through the middle, through the body of that medium. Whereas a surface wave is a seismic waves that a seismic wave that travels along the surface of a medium, and that has a stronger effect near the surface of the medium than it does the interior. And so body wave, going through the body, through the middle. Surface wave, only traveling along the surface of that medium. There's a big distinction there, and it's going to be really, really important when we start to discuss shadow zones and how Earth's interior affects the movement of seismic waves. As rocks along a fault slip into new positions, the rocks release energy in the form of vibrations called seismic waves. Seismic waves travel outward in all directions from the focus, not from the epicenter, but from the focus through the surrounding rock. Each type of wave travels at a different speed and causes different movements on Earth's crust. And that's why it's so important that we distinguish between these different types of waves, different types of body waves, different types of surface waves, because they're going to travel at different speeds through the Earth's interior and Earth's crust. Let's look at body waves more specifically. Two types of body waves, P waves and S waves. Okay, you're going to hear this a lot, P waves and S waves. P wave stands for primary wave, also known as a compression wave. It's a seismic wave that causes particles of rock to move in a back and forth direction, and here's the important part, parallel to the direction in which the wave is traveling. P waves are the fastest seismic waves and can travel through solids, liquids, and gases. Okay? Not all seismic waves can do that. And the more rigid the material is, the faster the P wave travels through it. Let's contrast that with S wave. So an S wave is, again, it's a type of body wave. These are traveling through the body of a medium. S wave stands for secondary wave or shear wave. It's a seismic wave that causes particles of rock to move in a side-to-side direction that is, the important part, perpendicular to the direction in which the wave is traveling. S waves are the second fastest seismic waves, right, behind P waves, but they can only travel through solids. And so, if an S wave if an S wave comes up against a gas or comes up against a liquid, that wave is going to simply stop. It cannot continue any further. Surface waves form from motion along a shallow fault or from the conversion of energy when P waves or S waves reach Earth's surface. Although surface waves are the slowest moving seismic waves, they can cause the greatest damage during an earthquake. Again, why? Because that's where humans are. That's where the buildings are. That's where the dams are, right? That's where the levees are. That's where humans are. And so things that happen on the surface have the greatest potential to cause the most damage. Love waves are surface waves that cause rock to move side to side and perpendicular to the direction of the wave. Rayleigh waves are surface waves that cause ground to move in elliptical or rolling motion. Okay, so we have side to side versus rolling. Okay, love waves and Rayleigh waves. All right, you guys are in class watching the video, so I'm not going to give you time to actually generate your own response. You can just listen to what I would have written to this question. Describe the two types of surface waves. So we just covered that. Should be pretty fresh in your mind. Rayleigh waves cause the ground to move in an elliptical rolling motion, okay, really kind of like loping, long rolling motion, whereas love waves cause rock to move side to side and perpendicular to the direction the waves are traveling. Okay, and the direction that these waves are moving or forcing the rock to move, they're very, very unique. Try to picture these different shapes of waves in your mind. Side to side, perpendicular to the direction that the wave is moving, okay, side to side, versus a rolling motion. You're causing the rock to move in very different ways, and humans, with the use of instruments, can perceive these differences, and they can use this data, for example, to locate the exact epicenter of an earthquake. And for the last slide for this video, seismic waves and Earth's interior. We're going to start to talk about Earth's interior next time. But here's the thing. By studying the speed and direction of seismic waves, scientists can learn more about the makeup and structure of Earth's interior, because we know that, for example, one type of wave can travel through solids, liquids, and gases, and can move through the body of a medium. We know that another type of wave can only move through solids. We know that a different type of wave can only move along the surface of a medium. And so we know all these things about different types of seismic waves, and we can use these different ideas to get an idea of what the inside of the Earth looks like. And you guys have heard of these things that I'm about to list, Earth's internal layers. You've heard of these things, the crust, mantle, and core. But how do we know that those things are there? Has anyone ever drilled down to see those things? Heck no. No way. You can't even get a probe down that. It's going to melt. It's going to break. It's going to be crushed. Something's going to go wrong. So the way we know about these things is not by having gone down there and looked at it. We know about it because of interpretation of data based on seismic waves. So I'll finish up with, in 1909, a scientist named Mohorovičić. Okay, I know it's a tricky one. From here on out, we're just going to say Moho, because that's actually a nickname that this scientist has been given since their death. But Moho discovered that the speed of the seismic waves increases abruptly at about 30 kilometers beneath the surface of continents. Now, 30 kilometers beneath the surface of continents, that's where the crust and the mantle meet. And so what Moho was able to say is, hey, when this seismic wave goes from traveling through the crust to traveling through the mantle, the speed of the seismic wave really, really picks up. It really increases significantly and suddenly. Now, by studying seismic waves, scientists have discovered Earth's 3 compositional layers. Compositional layers being the crust, mantle, and core. And we say compositional because what these different layers are made up of are very, very different. For example, rock in the crust, very high in silica. Rock in the mantle, we start to see more like magnesium and some iron, but still mostly rock. And then in the core, we see a lot of iron and nickel. Okay, a lot of iron and nickel. But the Earth is divided into other layers for different purposes. There are also 5 structural layers, and you've heard a few of these. The lithosphere, the asthenosphere, the mesosphere, the outer core, and the inner core, of which you've already heard of the lithosphere and the asthenosphere. Those are the 2 structural layers of the Earth's interior that are involved in plate tectonics. All right, Earth Science, that's where I'm going to leave you today for this video lecture. I will see you next period.